Good morning, folks. It is August 19th, 2022. Hope our creator is keeping you well and safe wherever you are in the world. Please make sure to hit that like button and share this across other platforms so we can let people know what's going on up at our sun's surface by all means, and the effects it can have here on Earth. If you happen to be new to the channel, please make sure to subscribe and hit that notification bell in case we have any critical future updates. Well, we're over here at spaceweatherlive.com, and over the past couple of days, we've had multiple geomagnetic storm releasing CMEs. Okay, with the result of the CME strike on the 17th. Now, granted, we didn't quite get our G3 class event that was originally forecast, not just by myself, but by others as well. But hey, don't give up. G1 and G2 storms are still very possible between now and the 21st. In response to additional CMEs, as we can see here, we've had several C-class and M flares in the past 3 days. And it typically takes about 3 days for these CMEs to arrive. And they are on the way. High latitude auroras remain most probable over the next few days. Now, in the past 24 hours, active sunspot region 3078 has produced 4 M-class flares and more than a dozen C flares, as we can currently see here. Most of the explosions have hurled all kinds of plasma into the outer atmosphere of the sun and passed it out into space, some in our direction, some not. Now, at the same time, these CMEs pretty much ended but with similar explosions hours earlier and later. This could cause additional grazing. CME impacts here on Earth between the 20th and between now and the 21st, extending the ongoing spat of geomagnetical activity. All right, so when we actually take a look here, I'm going to try and explain to you why it's so difficult to really kind of navigate all of this. Okay, first we're looking at all of this here. We actually had about from 4:20, well, actually, excuse me, from about 4:30 to about 5:10. Right about 5:10. So that's about 40 minutes of an M flare. That's pretty decent M flare. Okay, now let's come on over here to see our CME tracker. Let me explain to you something. Now, NOAA has already updated, Enlil has updated, this is the Enlil model, with an eruption off the western limb, which is blowing out that way. Now, this one was from yesterday. Now, if you notice here, in fact, let me zoom in a little bit here. As you can see here, okay, this is Earth, this is stereo behind, this is stereo ahead. Now, if you notice, you can see that there was this plasma filament that hit, and then this plasma filament that hit from the coronal mass ejections. Okay, so what you have to understand is when a coronal mass ejection leaves the sun, it's got a polarity to it. Okay, just like, you know, the sun has a north and south pole, we have a north and south pole. There's a polarity. A coronal mass ejection has a polarity. Okay, it is charged plasma. Okay, that's what it is. It's charged protons. Okay, so if you have one, let's say that this front one, and this is how what they call cannibal CMEs work. Let's say that you have this one here has more of a positive charge, and this one behind it has a negative charge. Okay, but let's say that they're closer to the sun as they're firing off. So if the one behind it is positive and the one in front of it has more negative, they'll click together. Okay, so they'll clink just like magnets. But if they're both positive and positive, they're actually going to push off of each other, just like the positive poles on a magnet. Okay, if you go to put a positive and positive end, they're going to push off of each other. But if it's positive and negative, clink, they'll clink up. And then when that happens, you're going to have extra positive, extra negative clinking together and causing more friction, which is how they actually become hotter as they get further away from the sun because of the extra friction that's going on in between. I mean, positive and negative polarities, it causes friction, causes heat, causes radiation, it gets hotter. That's just how it works. Okay, so when you've got multiples that are coming off, now here's another thing I've got to show you guys as we're looking at this. I don't know if we can, actually I might have to come on over to, no, is it here? No, let me come back over here. Let's actually do this. We'll actually go here for a moment, and I'm going to show you guys something. Okay, now this one here, this is at NOAA, Space Weather Prediction Centers. Now, let's say that, for instance, let's say that this one has more negative, and this one's got more positive, and this one's more negative. Let's say that they're firing off. Now, I don't know what this updated version, it's not accurate because they were firing off of this side. But let's say for argument's sake, they're going off this side. But this one's got more negative, this one's got more positive. So they're going to clink up. But this one is heavier, got more density than this one. So as they're coming out, this one will actually pull this one down because this one is stronger. And it's thicker and denser. So this is, if this one's the heavier CME than this one is, it would actually pull it down, so it would actually breeze by our planet and actually miss. Does that make sense? I'm hoping that makes sense. So if you got this one's a heavy, dense, thick, heavy positive one, this one's negative and this one's negative, it could pull both of them down to it as it goes off, getting it stronger and bigger as it's building and rolling along. Okay, but if this one's the stronger one and more dense than this one, it would pull this one up to it. So it could be a larger impact. That's one of the things I keep trying to explain. I probably didn't do a good job the other day of the complexity of all these eruptions, because some of it we just don't know. We don't know which one's positive, which one's negative, which one's more dense. It's really hard to gauge that, which is why this forecasting sometimes can be tricky. And I've had wrong forecasts. I have no problems admitting it, because this stuff is so tricky. Even people that have been doing this for 20, 30 years, they're getting it wrong too. I'm not the only one getting it wrong, so I don't feel so bad. Now, our probability forecast here from spaceweatherlive.com, we're actually looking at 75% for severe at high latitudes. Okay, active 5%, minor 15%. Okay, Friday and Saturday, we're looking at KP 6 for today and a KP 5 for tomorrow. And then, of course, we also know about this right here. For some of those who have watched my previous videos, the hemispheric power in, what is it? Gigawatts. You remember Back to the Future? 1.21 gigawatts? Oh yeah. Imagine once we start harnessing this stuff. Yippee-ki-yay. So what does it mean with high latitude? Well, let me show you. We'll come on over here to Solarham. These are high latitudes, okay? High latitude means up this way. High latitude aurora. Okay, so if you're aurora watchers, you should definitely be out. Now, South Pole, we're also getting it down here as well. I mean, when we're getting these storms, it affects both our North and South Pole. Okay, because we have a torus field of energy. So everybody knows about the magnetic lines that we have, and it comes in through the South and through the North Pole. So if you're high latitude, aurora watching, yeah, you're definitely going to have a good time over the next few days. According to the European Space Agency, over here at their Euphoria model, it looks like we did take a good chunk. We took about 55 centimeters cubed of plasma, which is pretty good. I mean, you can see it built up here. Now, if I actually click this and then pause her again, and then we back her up, yeah, it looks like about 55. And here, one of the things I do like about European Space Agency is they do show all of the multiple explosions catching up to each other like that. That's really a good thing. I think that's fantastic. I wish all of the models did that, because you can actually see right here, you can see where it kind of, what would be called the cannibal CME, the boom boom, and it just kind of builds and builds and builds and gets stronger. Yeah. And that's really a good thing. This actually is one of the more accurate models as far as forecasting on seeing if they're connecting up or if they're pushing away, because you can see here they're not connecting up. They're not connecting up. They're actually staying away from each other. You see that? Even though there's space getting between them, they should clink, and you've got the gaps. So that's a really good thing. Now, as we come over here to Space Weather Prediction Center, we're going to take a look at our flares, our X-ray absorption. This is our let me enlarge this for us here. And this was our M flare from earlier this morning, the one that lasted for about 40 minutes. It hit over in Asia. And then we'll see the rest of our little pops back and forth, our C flares. Africa gets it. Middle East gets it. Africa gets it a couple of times, and now it's going to be coming over towards us. So we'll see how this works out, right? Now, one of the things that's really nice about here at spaceweatherpredictioncenter.noaa.gov is you can come here and you can actually look at this. Last 24 hours observed maximums. Radio 1 and a G1. Okay? Right now, this is our latest. There's nothing. Everything's in the green. We're good to go. Okay? And this is predicted. A G2. Okay, now if we actually come down here, we can see what they're we can see what they're forecasting. For today, we're expected to have a G2 later on this evening. And then early in the morning tomorrow, a G1. Now, some of you are like, what are G1? What is R1? Well, you can actually come here yourself. Come on over, tap onto R1. R1, radio blackout impacts. See? Weak or minor degradation of HF radio communications on sunlit side, occasional loss of radio contact. Okay, that's what radio blackout is. Low frequency navigation signals degraded for brief intervals. Okay, now G1. What is that? You can look at this. Weak power grid fluctuations can occur. Minor impact on satellite operations possible. Migratory animals are affected at this and higher levels. Aurora is commonly visible at high latitudes, northern Michigan and Maine. Okay, so if that, I'm hoping this kind of helps answer some questions. And if you want to go further with it, you can actually come here and you can tap on the scales. And it'll come here and it'll tell you exactly what they all are, what it all means. So that way you guys can get the information yourself, so you know exactly what to expect when you see R1, R2, R3, R4, R5, or even G. Okay? Now we're going to end off over here on SDO. I normally don't go here. Normally I'm over on ISWA. But I decided I'm going to do it here on SDO itself. So here we're actually over at SDO. If you want a screenshot, you can see the website that I'm using. And you can see this is since the 17th. Now there's a couple things I want everyone to notice here. We're not just having flares. Okay, but we're also having filaments erupt. You see right here where my cursor is? This filament just erupts. See this? Whoosh. That filament just lets go. And then, shortly after that filament let go, bam! We had that flare and that chronomass ejection that we got impacted with. Okay, and that was on the 17th. Actually, that's not even here yet. That should be here either today or tomorrow. Now, if you watch, we have some more flares, not just from here. We have some here. But there's a filament that also is dancing right around here that also let loose. And I don't think this is part of that model. I don't know if they have this in there or not, but we're going to find out here. So here's one eruption. This was from yesterday. Look, I mean, and honestly, I think we're going to get some of that because if you see it, it's spinning out. It's spiraling. So when it comes out and it's spiraling like this, that tells me it's pretty much just throwing up and puking everywhere. Oh, it's going to do that, isn't it? Oh, yeah, it is. Okay. I don't care for that. That's one reason I don't like SDO. Then we had our eruption here that it showed. Now watch this. If you guys are watching, watch right around in here. You're going to see a filament eruption. Whoop. You see that? Right here. See that filament? Comes right up whoosh, and snaps up. You see that? Whoosh. And there was no flare here whatsoever. And then we had our flare here with our chronomass ejection coming towards us. Now, it's funny. It's coming this way and not going this way. Why isn't it just going straight out? Why is it coming right at us? Well, because you've got two planetary magnets. Don't forget, Saturn is right behind us. So you've got the magnetic pull between Earth and Saturn pulling in this direction. Now, why did the big one go off over here? Well, because Jupiter's over here. And once this sunspot group gets over here, you'll see it firing off over towards Saturn. Let me show you again real quick. Here we are, planetstoday.com. So we've got Earth and Saturn. We got the magnetic connection line, the magnetic pull between both of our planets pulling at the sun. So this is why it's even though it's slightly over here, it's still firing off in our direction. And then the one that was over on this side, the big one that fired off, well, you've got Mars in this direction, Jupiter and Neptune, all these magnetic pulls in this direction. So yeah, and as we start getting, like I said, folks, we're just getting started. Once we start getting over into this direction, yeah, then it's really going to get exciting. All right, now to finish up on this guy, and then I'm going to let you guys go here. Here's our liftoff again. We had that fire. So now you guys kind of understand a little bit why we're getting these eruptions on this side and why they're firing off this side. We've got the planets pulling. It's magnetism. It's all about magnetism. And one of the other things I'd like to explain about magnetism is that is why our planet is round. We live on a planet, not a flat Earth, not a crater Earth. We live on a flat, round, or not a flat, but a round globe. Excuse me. Just like our sun is round, it's because of magnetism. Magnetism is why we are round, why we have a torus energy field. If we were a flat Earth or a crater Earth, we would not have a north and south polarity coming from our planet. Period. I hope this helps to iron things out for some people. So keep your eyes open, folks. No fear, and remember that love is the only way forward. So, wolf out.